principle is one of the key things that separates classical and quantum physics. And what I want to show today is that actually there are certain situations in which when you try to apply the uncertainty relations that we had until now, that actually you cannot apply them. And so what we've basically done is come up with an extended relation which implies in the presence of quantum memory. So essentially all of the uncertainty relations that we knew of before this only apply to observers with classical memories. And I'll explain what that means more precisely. But basically the idea is that one of the key things will be that if you allow the observer to have a quantum memory, they're very much more powerful in certain situations. And not only that, but we'll derive a new uncertainty relation that covers the case of quantum memories that weren't covered before. So before that, I'll just give a quick summary of a few previous uncertainty relations. So, I mean, the one that everyone will be, of course, familiar with is the first uncertainty relation of Heisenberg. And its generalization to other observables is also very well known. So, for example, whatever this is. So where you bound the uncertainties in terms of the expectation value of the commutator. So this applies for any observables, whereas this is just for x and p. Now, so this actually was derived by Robertson already in the 1920s, 25, I think. But actually these aren't, or this, certainly this last relation has been heavily criticized, first I think by David Deutsch in the 80s. And he makes the point that, I mean, first of all, this thing here depends on the observables R and S. So in particular, you can just arbitrarily change the amount of uncertainty you appear to have by just scaling how you label the outcomes of the observable. So it's not a very natural measure of uncertainty for that reason. And secondly, actually the bound here, I mean, it's got this expectation here which depends on the quantum state. I mean, this means that where these are the operators, you take the expectation value for that particular quantum state. And of course, actually, if you try to make a state-independent bound from this, I mean, you can, of course, add here that it's bigger than equal to the minimum over all states. But unless you have, but for any finite valued observables, there will always be 0 here. So actually, this bound is not very useful unless you have, if your observables are finite valued. And it's kind of clear because this is a standard deviation, and there will always be a state at which this is 0. So actually, we think of more general ways to look at uncertainty via entropic uncertainty relations. I haven't said yet. So here the uncertainty is measured by the standard deviation. So this delta R is the standard deviation, which means that you have some observable R, you measure it loads and loads of times, and you look at the standard deviation of the distribution. But here, I mean, in the entropic uncertainty relations, we'll measure it.
I mean, so the criticism that you sort of seem to be also making is that, that's state dependent. That's what's wrong with it being state dependent.
There's nothing wrong with it being state dependent in some sense.
If the uncertainty is the expectation, is the standard deviation, then the standard deviation is in a state. So.
Right, but of course, I mean, okay, you could just evaluate this for that state, right? So the advantage of using an the advantage of using an uncertainty relation is to have some bound which is more general than that. I mean, such that you don't care what. I mean, it was very useful if you can have a bound that doesn't depend on the state, that you can just say whatever state we have at this point, we can apply this relation.
Okay, so I'm trying to find out what you mean by uncertainty relation.
Well, okay. I mean, that will become, maybe I can leave that till I'll introduce a very specific scenario in which the uncertainty relation comes up in a minute, and maybe that will make it clear. So,
next, a related question. Is it the case that you're looking at those uncertainty relations which express a trade-off in the predictability between two counterfactually possible measurements?
Right.
So the idea is that if measurement 1 has a certain amount of predictability, then measurement 2 will have to be less predictable.
Right. So let's maybe take the case of Pauli X and Pauli Z. Suppose I'm going to measure either Pauli X or Pauli Z on a particular quantum state. I'm going to measure one or other of them. And this is supposed to tell me that the standard deviation, if I measure one of them, multiplied by the standard deviation if I measure the other one, is bounded by this. Okay. Or is that a bit clearer? Or?
So you can say that there's a failure of that uncertainty relation to express the trade-off that we know exists.
Right.
We know that both Z and Y, there's no state that makes the outcome both Z and Y predictable. And yet this uncertainty relation fails to capture that fact because it says, oh, a Z eigenstate makes the variance of Z equal to 0, so there's no constraint on what the product is. Whereas the tropic uncertainty relation does so.
0 times anything is 0. So.
Right.
So the point is,
but
there's something that hasn't been captured by this uncertainty relation.
So suppose it was the plus instead of the multiplication. Suppose it was the sum is lower bounded by something. Then I mean we can hope to capture uncertainty even if the uncertainty is 0 for one observable, it is greater than 0 for the other, and the sum would have captured it. So we want something like that.
Yes, of course you can argue that this captures it when you have the state in there. But if you want, if you minimize overall states, this will be 0 for the example that Rob gave. And like you say, you might hope that the sum can be bounded in a non-trivial way. But there's certainly more than this to what we can say about uncertainty.
I'm trying to get a feeling for what your intuition is about what you mean by uncertainty. That's why I asked the question, and you say that you will develop it as you go along. So
yes. Okay. Thanks. So a way of replacing this has been developed using, a natural measure of uncertainty instead of the standard deviation is the von Neumann entropy. And a series of work sort of culminated with the final statement in the 80s by Masson and Fink, which looks like this. So I'll explain what this means. So R and S are the two observables. H is the, so this is the Shannon entropy of the distribution over the outcomes. So essentially what it means is we have a quantum state ρ, and we're going to measure observable R, which corresponds to a series of basis vectors like this. So the observable R, I can just write like this. Okay, and if I measure on state ρ with R, if I get outcome, this generates a probability distributions over the outcomes. Like this, and this is the Shannon entropy of this probability distribution. That's the meaning of this.
That doesn't depend on the eigenvalues at all.
It doesn't depend. No, it depends only on the probabilities of the outcomes.
Right. It doesn't depend on the little r at all.
Right. Exactly. So that's one of the criticisms of this that Deutsch raised, that this depends on the value of little r, and that's just an arbitrary label. So by going to von Neumann entropy, now it doesn't depend on, I mean, yeah, you can arbitrarily scale the R whatever you like, and it's just depends on this probability distribution.
On the other hand, if all the R are degenerate so that R is completely predictable, so that's the identity matrix,
Right.
then this H of R would still be non-zero. So it's not predictable because you've got a probability distribution over the eigenstates.
No, but if you, well, it depends. I mean, do you do a rank? If you do a rank, if you measure if the observable you measure is just the identity matrix, then it always gives that outcome, and so the entropy is 0.
Well, I'll make it, R identity plus then each one of these guys is a random variable of 10 to the minus 9 to 10 to the minus 10 to the minus 10 to the minus 10. So the eigenvalues are distinct, but completely irrelevantly distinct.
Right. But you still have different, I mean, if these label different outcomes, then that's right. Even, yeah, I mean,
R is completely predictable. I mean, to within 10 to the minus 10 to the minus 10 to whatever.
But
I don't.
Is if you just go and say we do the measurement, like a UVM measurement, we just define the outcomes. And I mean, the observable notation doesn't make sense actually, that point, no one cares about it.
Yes, it doesn't matter.
Instead, you just prescribe the measurements of UVM.
I mean, I measure these, right? I measure in that basis. So you tell me the basis you want to measure in, I measure in that basis, it produces a probability distribution over outcomes. So if your basis, I mean, more generally the measuring basis, you could measure a POVM. And what I said before is if that POVM contains the identity, then the entropy will still be 0.
But I'm just saying that this thing doesn't capture his notion of predictability of R.
Why not?
The way you said it, Roger, is not generic enough. Instead of picking on a basis, you should have chosen a projective value measure. Then, if there are degenerate eigenvalues, you can say the probabilities are just defined as trace rho times the projector onto that associated eigenspace. And I think
Right.
No, but if they're almost degenerate,
yes.
okay, then of course it doesn't matter whether they're almost degenerate or not degenerate by huge amounts. This measure doesn't give a damn.
But it doesn't matter what these are at all. You just need to know
That's what I mean.
what these are. So why is that a problem?
This isn't capturing his notion of predictability of R.
I think it is. So where what you just said is that if you're talking about a Hermitian operator, then I think there is a discontinuity when you go from degenerate to non-degenerate. Because if I express that in terms of the projector value,
Of course, but not in terms of projectability, and not in terms of predictability.
Predictability of events of the numbers. Because R is a number, but I mean, that's just something you make up in our head.
Yeah. Yeah, I mean, maybe forget this. This is maybe confusing.
It's something you measure physically. No.
But I can label it what I want, right? I have a device that's a measuring device. I choose what to measure, and it has a bunch of output ports, like 1 to 10.
Right.
But maybe I can just relabel them 10 to 20. That's changing R.
Not if I'm doing physics. If I'm doing mathematics, I can. If I'm doing physics, I want to measure real physical quantities that have physical consequences to them.
Right. But the only thing that matters is the probability of the different outcomes. So even if you
I know in this definition, I agree with you that that's all that matters. And I'm saying that doesn't seem to capture the notion of predictability that he was talking about.
Okay. Yeah, I don't fully understand that. But
all that's relevant is the probabilities of different outcomes. And if you ask, what about a Hermitian operator determines the probabilities of different outcomes? The answer is only the eigenspaces.
I agree.
Irrelevant what the eigenvalues are. And if two eigenvalues are close to degenerate, it doesn't matter. It's still.
I agree. That's precisely the point I'm trying to make.
So why do you say it doesn't capture predictability?
Because it's predictability of R that one is interested in physics. How well do I know what this dynamical variable's values are?
Ah, I see.
That's what I would call predictability. I mean, I don't care about what state they have. That's not
Roger
physics.
has a different notion of predictability. He's talking about the predictability of the outcome.
Well, you were the one that introduced that.
I think Roger agreed with me.
Yes,
that
yes.
That's the notion he wants to capture. So it's not predictability about the value of some permutation operator, but predictability of the outcome of some experiment that he's interested in.
I'm going to measure some observable R. I want to know what the distribution, or how uncertain I am about the distribution of the possible outcomes.
Yes.
So in your case, where you have two very, very related things, I'll just assign those different outcomes.
Yeah, I know you would, but physically they don't. I mean, I wouldn't. They're so close together that as a physical outcome, I would not say that they're different.
Okay, but then you should define a window.
Okay, continue. I mean, anyway.
Okay.
Sorry, can I just ask, what is C?
Yeah, so I haven't explained what C is yet. So for two observables R and S, if I characterize them in terms of these projections, C is the maximum overlap of this R and S. Okay, so it's some measure of how well these operators commute. So if these operators completely commute, then this overlap will be 1, and then this log will be 0.
That just says that if one single eigenstate is the same, then that's 0.
Right. So it's not, I mean, it's not going to be tight for all cases, it's bound.
So that seems to have the same rejection as yours to that delta R, delta S.
Well, this doesn't depend on the state. This just depends on the observables.
No, but it depends on the eigenvalue space, and if the eigenvalue space happens to have one single, I mean, you suggested maybe we could take the minimum of that right-hand side.
Right.
Delta R, delta S, and then you said that was, I didn't like that because one can always find some state for which that's 0.
Right.
And in this case, if there happens to be one set of states out of 10 to the 99.
And one for the, I mean, this depends on the observable, not the state.
Right, if there happens to be one set of eigenstates of those two observables that are in common,
Right.
out of 10 to the 99, even though all the others have minimal overlap, then this thing is 0.
Yes, that's right.
Okay.
Yes, I mean, the kind of applications we're thinking about are things like quantum key distribution, where usually you have like you're working with qubits and you have two observables and things like this. So these concerns, I mean, there are concerns with this. Like, it's not clear how to generalize this, for example, to continuous variables and things like this. So at the moment, we're really thinking of finite Hilbert spaces. Okay. So is that clear at the moment? Okay, so although this relation is not tight in all situations, I mean, there are situations in which it is tight. For example, if these are complementary observables. So if these are like Pauli X and Pauli Z, then this overlap goes like, maybe I should write it out. So just for an example, Pauli X and Z, then we get C goes like 1 over the dimension, and we get the bound. Well, for Pauli X and Pauli Z, the dimension is just 2. So we get the bound like this, okay?
Log to the base 2.
Yeah, sorry, log is to the base 2. Okay, so we sort of take this to be the standard standard uncertainty relation, entropic uncertainty relation. And now what I want to show is that there is a case where it doesn't apply, or where we cannot use this uncertainty relation to where we might hope to use it. So now I'll introduce the following game. So just call it the uncertainty game. Okay, and it works like this. So it's 2 players, Alice and Bob. So Bob's over here, Alice is over here, and what happens is as follows. So the first step, Bob creates a particle in a quantum state of his choosing. Okay, he creates any quantum state he likes. Okay, and he sends it to Alice. Okay, then step 2, Alice measures one of 2 observables, either R or S. And what I should have said is that those were pre-agreed. So Bob knew those before. He knew what R and S were going to be before he chose what state he wanted to create. Okay, and then Alice announces her choice, but not the outcome. Okay, and then the goal is for Bob to try and guess what her outcome was. So, Bob tries to guess Alice's outcome. Okay, so this is maybe makes it clear what kind of uncertainty you're thinking of. So moreover than that, you can think of Bob trying to minimize his uncertainty in terms of this. So the question is, can Bob always win the game? Okay, and if you try and apply this relation, you'll come to the conclusion that, I mean, this relation can't directly be applied to this situation, but you might hope that it could. And if you try to apply this relation, you'll conclude that Bob, I mean, it looks like Bob shouldn't be able to win the game, right? Because let's suppose R and S are X and Y, X and Z, then you might say, well, it's impossible from what I said right at the top there, h of x plus h of z is bigger than or equal to 1. If Bob can always win the game, the left-hand side of this inequality should always be 0. So it looks like there's no way for him to win the game, right? So he can win it sometimes, of course, because he can always, he can create an eigenstate of Pauli x and hope that Alice picks x, and then he can always guess correctly. But if he creates an eigenstate of Pauli x and she measures z, then then he just has to randomly guess the outcome. Okay, but in fact, using entanglement, Bob can always win the game. Okay, and what he has to do is entangle the state he sent to Alice with one that he keeps in a quantum memory. So roughly, I mean, what's the best way to say this? So if he creates the state this, where the first space is kind of in his memory, and then this is the one he sends to Alice, then because that's exactly equal to this, then once Alice announces her basis, Bob just does the same measurement that Alice did. Okay, so this is not maybe a big surprise, but it, of course, shows that there are some scenarios that we have that this uncertainty relation, or the uncertainty relations we have up to now, cannot be applied to. Okay. Okay, so now I'm just going to give the new uncertainty. Yes, yeah.
So this is for the special case of x and z. What about general R and S?
Yeah, so this actually always works for any R and S. So there's always, it's not exactly the same measurement, but he actually does the transpose measurement. Okay. So for any R and S, there's a measurement on the other side that.
As long as it's projective measurement, isn't it?
Right. Yes. Sorry, for projective measurement.
But for POVM measurement, you can create some products.
If you do this times, this key UVMs elements, cannot create a specific outcome from that. That was like a counterexample of humans.
Yes, yes. So this.
But that's a little bit of cheating. Because
Oh yeah, sure, absolutely.
I would say doing this is cheating, because the rules said he was supposed to send a particle in a quantum state of his choosing, and he has no idea what quantum state he sent to Alice.
Well,
He's got entangled.
well, he knows the state of the entire system.
No, but he doesn't know what he sent. He said a state of his choosing, which he sends to Alice.
Okay, this is maybe a language issue, but okay. So the new uncertainty relation. So I mean, the problem with this original uncertainty relation is that it's not conditioned. I mean, this is just the entropy of S, whereas really we want something that, I mean, really we want to condition on what Bob might have. So really we want an uncertainty relation like this, where this is the conditional entropy of the outcome R given B, which is a system Bob holds. So roughly speaking, this entropy, yeah, I mean, it kind of takes into account the fact that Bob holds something. Okay, and then this is bigger than minus log 1 over C plus, and then there's an additional term, which is the von Neumann entropy of A given B, depending on the state he sent. So this is for a state rho AB, which means the A part is sent to Alice, Bob keeps the B part in his quantum memory. So this is state dependent, yes, in the sense that this entropy here depends on state, yes. Yeah, so we don't get around all of, I mean, those were Deutsch's criticisms of the original relation. But ideally we would not like that, but yeah, we can't get around that.
So on the left-hand side, what entropy is that?
Right, so this is the von Neumann entropy.
Classical is one.
Conditional, yeah, so hang on a sec. So this is the conditional von Neumann entropy of the state after measurement. So if I take rho AB and I measure R, right, this produces this. Okay, so this does this, and this, the final state then will look something like this. Okay, so it's this means the von Neumann entropy of this state, basically. Okay, and similarly H of S given B, whereas H of A given B is just the von Neumann entropy of.
As a conditional, you mean the joint minus the entropy of B.
Right, so H of A given B is equal to H of AB minus H of B. Okay, yeah.
Could you make this state independent by just taking the supremum over choices of rho AB on the right-hand side? I mean, in the whole thing.
I mean, if you do that here, then I mean, there's always the maximum entangled state has this equal to minus log D. So then you'll just get a trivial bound 0. So actually, I mean, the case that I explained here, where Bob can always win. So there we had this relation H of X. So we had this relation here, and then if I'm going to add this H of A given B, I mean, for this maximum entangled state, this is minus 1. And so then I actually get, this is bigger than or equal to 0, which is a trivial bound, because once these are classical, even conditioned on quantum information, these are always positive. So it's not, yeah, in general, you don't want to do that. Okay, so now maybe just say, so basically what this means is how well an experimentalist can predict the values of two observables depends not only on how well those observables kind of overlap or how, what's the word? How complementary they are, but also on how entangled that experimentalist is with the thing they're trying to guess. So that's kind of the main sort of new result. Okay, so what I could do is give a short sketch of the proof for a simple case. I mean, the full proof is actually very complicated, but for a simple case, I can that will give a sort of idea of how it works. So first thing, so actually the case where the observables are complementary turns out to be much easier. So we'll consider complementary observables. And actually this part was first proven by Joe Rennes and Jean-Christian Boileau in the paper which kind of conjectured a relation similar to this. So I should start by defining some operators. Okay, and DS. So I start by defining these operators, which are in some sense generalizations of the Pauli operators. So this was the basis this is the eigenbasis for R, and then we just put complex roots down the diagonal in that basis. So this is like a generalized Pauli Z, and this is like a generalized Pauli Z in the other basis. But if they're complementary, then it's like one is like Pauli Z and one is a bit like Pauli X, if you want to think of it like that. Sorry, what's?
Little r.
Little r is the index over the outcomes. So I had a measurement with outcomes, which I can label with little r, which goes from 1 to the total number of outcomes.
So these aren't Hermitian.
No, these have got, these aren't Hermitian.
So they're not really observables.
Wait, they should be Hermitian. I mean, these are not the observables, but I mean the observables are formed by these. So I can just introduce these operators. Okay, it's not, but I guess they don't. Yeah, maybe the analogy with Pauli Z is not so clear for that part. Okay, so now I want to write this, the part, where is it? So the map corresponding to the measurement here, I want to write in terms of these dRs. So I can write it like this. So rho AB, so this is the map where I just do the measurement on R. This takes rho AB to the state. So I can just consider this map. So this is dr to the A, tensor identity, rho AB, and then dr to the minus A. Okay, so it turns out that that's the same as this. That's another way of writing this this map here. Okay, that's maybe not immediately obvious, but take my word for it. Okay, and now the nice trick. Okay, maybe I have to erase. Okay. So then we're going to consider the following state of 4 systems. Okay, and it looks like this. Okay, so we just consider this state, and you'll see why this is such a useful state in a second. So they're just sums over all the outcomes. I mean, they're just summing. You mean in this relation? So
on that next line, you've got those A and B that you're summing over. I don't know what those A and B are.
So these are just orthogonal bases on an additional system that I introduce. So there's some Hilbert space. I can just introduce an additional Hilbert space, HA prime, and little a is an orthogonal basis on that Hilbert space. And similarly,
I guess it's important that your displacement operator D exponentiated to the little d dimension space is the same as.
right, it goes back to
The
the identity.
original one.
Yeah.
D plus 1 should go back to.
Right. So when I raise it to the D, I get identity. I think.
Particularly RD identity. Yeah, I'm not sure, but it forms a cycle such that when I sum over all of them, I'm kind of back to where I started. Okay, so the useful thing about this state is that when we discard certain parts, we get exactly what we kind of need on the rest. So let's consider this entropy. So basically what I want to do is consider entropies of this state omega and relate them to the entropies I need. And these ones here are going to be the ones I need, and these are of the state rho. So that's kind of the idea. Okay, so what is this entropy? Well, if you look at this state, it's kind of, on this part, it's just maximally mixed. On these first 2 parts, this is the dimension of these systems. Okay, so I get 2 log d, but basically the idea is that given A and B, I can kind of undo this. I mean, this is like starting with rho AB, and then we can think of like doing some operation on it. But if I'm given access to the AB space, I can kind of undo that. So it actually turns out like that. Maybe I didn't explain that very clearly, but that's sort of the idea. It's the entropy of A prime, B prime, A, B. There's no colon there?
No, there's no. So essentially, if I have these spaces, I mean, basically this state is, entropies are invariant under unitary operations. So I can do a unitary operation on this to like conditionally undo the action of this ds and this db. Okay, then I've just got this tensor rho AB, and these are maximally mixed. So okay, then similarly, I do the same. So for this, and this one gives me log D plus H of SB of rho. So let's just see what happens there. So now I've lost B. So imagine if I've lost B, that means I can't undo this relation here, this S relation, but I can still undo the R relation. So I can undo the R relation. Now I've got the S relation, but the S relation, okay, it's analogous to this. It corresponds to this measurement. So I'm going to have this sum. Okay, then, I mean, this goes away, and I've got this sum here over B, and it corresponds to doing the measurement. Is that kind of clear, or no? It's what? It's clear, yeah, okay. Or is everyone happy? So I said this quite fast, maybe. So anyway, you continue like this. So H of B prime AB for omega. This is log D, and this is where we use the fact that the observables are complementary, because that allows us to commute. I mean, because these are complementary, they actually anti-commute, but because I've got two of them, when I do both, they commute, and so I can do the same thing. So this is why the proof that I give now won't hold for all observables. Okay, and then the last part that I need is H of AB of omega, but that's so that's log D plus HB on rho. Okay, so there the A system becomes maximally mixed. I don't know A or B, and that's like first measuring in one basis, then measuring in the other basis, and then I just get a maximally mixed state on A, but I've still got B. Okay, so that's, maybe that was a bit fast, but.
So that should also be H of A, because what distinguishes A and B?
In the state omega, this is tensor, so this is identity on B. So this measurement here only occurs on the A system. So B is left untouched, so it's still.
So here also you're using complementary observables?
So this,
the last one
I guess it doesn't matter there for the last one because. Oh, right, yeah, it might not be identity. Yes, yes, yeah, you're right.
Mixing A and decoupling it from B.
Yeah, so yeah. I mean, the fact that I get log D is because they're complementary.
And
yes.
it's decoupled, so there's a plus.
It's decoupled from B.
From B, yeah.
Yes, yeah.
So the maximal mixed state on A tensor, the marginal on B.
Right, exactly. Okay, so the next thing will be to use strong subadditivity on the state omega. So the result actually now follows just from that. So what does strong subadditivity say? Well, I can write it like this. So if I consider this quantity, this is the entropy of B prime given A prime AB, and that is always smaller than the entropy of B prime if I throw away one of these systems here. So I throw away A prime, I get this, and I can write that as B prime AB minus the entropy of AB. Okay, so this just states the very intuitive property that if I lose access to something, I become more uncertain about. So if I've got access to A prime, A, and B to try and guess B prime, if I lose access to A prime, it just makes it harder for me to guess B prime. So that's a restatement of strong subadditivity of the von Neumann entropy. Okay, and now all these parts we worked out above, and maybe I'll take my word for it that if you plug them in and rearrange them, you get this, this new uncertainty relation. Okay, so that's for the case of complementary observables, and actually it's not easy to generalize this directly. So the proof, the more general proof doesn't directly use the von Neumann entropy, and kind of the problem with the von Neumann entropy is that it involves involves kind of all the probabilities. So actually the main proof uses the min and max entropy, which are somehow, well, I don't know, maybe I shouldn't say too much about this now, but they're somehow simpler versions in the sense that they don't depend on all the eigenvalues. And by that property, it makes some steps of the proof easier, and others become a bit harder. But we still use the technique still uses the same omega state, and properties like this for the min and max entropy kind of go through the same. So actually what we end up proving is a statement that looks roughly like this. Okay, and then there's some epsilon term. And it turns out that these entropies tend to the von Neumann entropy in the IID limit. Well, maybe I'm saying.
So you mean you don't actually prove this, but you prove this?
No, I mean the statement, yeah, I mean from this you can derive this straight away by taking the.
Or you take IID.
Yes. So, yeah. Actually what we prove is actually this. And then if you take, so this is for the state rho, and then we use the property, this property, rho tensor n. So if you take IID copies of it, 1 over n, then take n to infinity, then this is actually the von Neumann entropy. And that's the same with this. Anyway, maybe this is too technical to go over all the details now. So that's just a rough version of that.
So
Yes.
to be clear, this uncertainty relation written down holds for all pairs of observables, not just complementary ones.
Right.
And the way you prove it is by first proving that and then taking this.
Right. Yes. But this only holds for well, this doesn't hold for POVM valued observables only. Well, no. Or actually,
Does that only hold for projective as well?
this.
Yeah.
Yes, this is. So it's actually for any. It doesn't hold when the rank of the POVM elements is more than 1. So I think it works for rank 1 POVMs as well, but not for higher rank. But actually, there are now versions since that have been proven that extend to that case for a slightly different relation, which I'll explain now, maybe. Okay, so the basic implications, maybe I should just so first of all, if A and B are maximally entangled, then we get a kind of trivial bound. For any observables, because H of R given B plus H of S given B. For maximally, if A and B are maximally entangled, this H of A given B is minus log D. And I get this. But this thing, I mean, this is always bounded by 0. So this can never compensate for this sorry, this should be minus. So this side is always negative, actually. Okay, if A and B are not entangled, so then we have this, and actually we can then rederive the mass-and-nothing relation that's now gone, but it's actually a slight strengthening of it, because the mass-and-nothing relation is kind of without this H of A, so we can actually have a slight strengthening even in the case of no entanglement. And of course the most interesting case is where A and B are entangled and perhaps not maximally so, and then this is really a new bound, and you have to you use this term to compensate for what's happening there. So this plus HA of A given B is in general negative, so it's actually making the bound on the right hand side smaller. So we just to suggest a few applications. I mean, one is to use this kind of as a witness of entanglement. So if ever you can play this game or some analogous game, then if you can show that these things, if you can beat the mass-and-nothing bound, then you necessarily must have this thing being negative, which is basically proves that your rho AB is an entangled state. So that's one application. Maybe the more interesting, or I could just in the last few minutes explain a quick application to QKD. So the key rate in quantum key distribution. So actually using this relation, and another relation of Devatak and Winter, we can show, we can quite easily derive a bound on the key rate in quantum key distribution. So what happens in quantum key distribution is basically, so let's consider so-called entanglement-based protocol. So we have two players, Alice and Bob, and there's an eavesdropper E. Okay, and in entanglement-based protocol, you assume that Eve has created some state, rho A, B, E, and distributed it to Alice and Bob. So in other words, Alice gets the A part, B gets the B part, and E is in general some part that the eavesdropper keeps. And of course, what Alice and Bob want to do is to make sure that this state is virtually unentangled with the eavesdropper, so that then the eavesdropper will have almost no knowledge about whatever key they create. Okay, so let's consider, so we start with this bound of Devatak, or maybe I should first, before I do that, I'll just explain a rewriting of our uncertainty relation. Okay, so it turns out that the uncertainty relation is equivalent to this. Okay, for any rho A, B, E. So for any state on a tripartite system between Alice, or just tripartite system on A, B, E, turns out we can replace this. We can, in some sense, move this onto this side and replace it by an instead condition on system E holds. So I won't go through that now. It's not very many steps. But this is kind of an amazing relation because it says that it allows us to use information on Alice and Bob, or it allows us to use data between Alice and Bob to conclude something about data between Alice and Eve. And that's actually one of the key things that's needed for quantum key distribution, because once this state's being distributed, Alice and Bob never have access to Eve's system, so they have to use data only available to themselves to try to infer something about Eve. And once we've written the uncertainty relation in this form, then it allows us to directly do this. And this was the form that I was going to say with relation to your question, which I now forgot. But maybe you did.
I was asking POVM.
Ah, right. So this is the form of the relation, that how it looks when it has been extended to arbitrary POVMs. And the equivalence is not, doesn't follow for arbitrary POVMs. So these two relations for projective measurements are completely equivalent, but they're not equivalent for POVMs, and this form of the relation has been since extended by Coles and others to a relation for POVM. Okay. And possibly this is the more useful form of it for applications, actually, although that in some sense remains to be seen. Okay, so now what do I want to do? Right, so now using this result, and basically we combine this with the result of Devatak and Winter, we'll get a very simple proof of, or a simple bound for the key rate of quantum key distribution in a kind of IID setting. So it's maybe not it's not the final goal one would hope for a key distribution result, but it's actually equivalent or a slight generalization of the Shaw-Preskill key distribution rate that came out in 2001, I think, or something like this. So Devatak and Winter show that the key rate is bigger than h of r given E minus h of r given B for some state, for any state rho A, B, E. So if there's a state rho A, B, E, and so after some measurement, this will become rho B. So for a state of this form, it turns out, and this is the result we're quoting, that you can bound the key rate like this. This means that if you have an asymptotic number of copies of this state, then the rate at which you can process, by processing them afterwards, the rate at which you can distill key can be bounded like this. Okay, and it's kind of intuitive in the sense that, well, if you think of this entropy as saying how uncertain is Eve about, this sort of says how uncertain is Eve about R, and this kind of says how uncertain Bob is about R. Now, if you imagine a key distribution scenario, what has to happen is that Bob has to become absolutely certain about R. So this is, roughly speaking, the amount of communication that Alice has to send to Bob so that he knows the key perfectly. But of course, Eve hears that information, so that kind of subtracts away from hers, and then this is what's left. So, okay, that's really very intuitive, but actually the entropies are such that it does work out like that. Okay, so now if I use this and our relation, I mean, what's the hard thing is to sort of find a bound for this, but actually using this relation, it basically means that we don't need to, because instead of bounding this, we can just, and we can transfer the E part to the R part. So instead, I will get h of S given B, or sorry, I get log 1 over C minus h of S given B minus h of R given B. Okay, and I can also make this bound. I mean, to really compute this bound, both Alice and Bob are going to have to measure, and this is actually under measurement. These entropies can only get worse. So actually, if Bob measures in the same basis as Alice, we can just trivially apply this relation. And this is basically a generalization of this is slightly more general than the bound derived by Shaw-Preskill for the key rate. Of course, in real quantum key distribution, there's no justification for this state really being distributed in an IID way. So it's not actually the ultimate result you would eventually like. And to get that ultimate result, we'll need an uncertainty relation actually in terms of min and max entropies rather than von Neumann entropies. And actually, very recently, a generalization has just appeared. So I guess that's nice. Okay, well, I think maybe I should stop there. I don't know if that seems I've gone over.
Questions for Roger? Yeah, maybe I'll start with one. When you're describing the original uncertainty game,
Yeah.
I was surprised that you didn't put a connection with EPR, because it's ultimately the same sort of experiment that Einstein-Close-Merlin suggested for proving that you can't imagine quantum mechanics is so complete and local.
Right.
Because
Yes.
You can predict either X or P, to two complementary observers by having an entangled state.
Right. So Bob holding that. Yeah, Bob has the ability to predict both, and so they would say probably that there should be an element of reality associated with both of them.
By virtue of locality. But the more modern development of that is people have looked at steerability. So people have been thinking about which ensembles of states can you prepare the distant system and you do different measurements. And people have written down basically constraints on the joint steerability. If I can steer to one ensemble, can I also steer to another ensemble? With a maximally entangled state, I can usually steer to anything I want.
Right.
But if you have a non-maximally entangled state, then there'll be limits on the steerability to various different things.
Right.
So I wonder, is there a connection between your uncertainty relation should also be a steerability trade-off?
Right. I guess that's the case. I mean, there you have to. What would you have to do? You'd have to look at what state you have, and that would give you the entropy of A given B, the kind of bit on the right-hand side, and then, which would give you this log D if it's maximally entangled. And then that would certainly give you a bound I guess people don't measure steerability with these entropies usually, but that would seem to be a reasonable. So I guess it directly tells you about that. I'm not sure. Maybe it wouldn't. Yeah, I don't know. Maybe I shouldn't speculate now, but maybe it wouldn't give you the best steerability bounds in general, because I'm not sure how well this drops off if you consider an arbitrary state. Like, I could believe that it's not maybe the best way to measure the steerability, but yeah, maybe I don't want to say too much on that now, because I haven't really thought about it.
Another question. How easily can this be generalized from 2 counterfactual possible measurements to 3 or n?
I don't know. It's not. Yeah, it's not immediately obvious how to use the same proof technique. I'm not sure of how to use the same proof technique. I mean, one of the sort of, one way to look at this maybe is to use some kind of duality relation. So this thing is actually always equal to 0. that just follows from the Schmidt. Well, this is somehow a duality relation for the entropies. So for any pure state, at least, this is, sorry, for any pure state, this is always equal to 0. And then, so one way to see that there should always be uncertainty relation is now to think about measuring these and seeing that the entropy must always go up when you measure them. And then it's just a question of sort of how much does it go up. And that's kind of what the sort of more recent proofs, actually, since this of the min-max version are kind of based on. Because the min-max also satisfy this relation. And it's then, yeah, I mean, this doesn't really answer your question very well, but to use this kind of proof technique, it's not really clear how one would introduce additional measurements, but I haven't really thought about it.
Other questions? All right, thanks much again.
Yeah, there was this paper by Ambinis, actually, he had a lot of